Hello everyone, allow me to welcome you at this talk of Ekaterina Ilin called An Altruist Motive to Look at the Stars. Ekaterina is a postdoctoral researcher at Leibniz Institute for Astrophysics in Potsdam, and she will be moving to Groningen soon to pursue similar objectives. The talk will be about 40 minutes, and please, if you have some questions, use the swap card to, and we can answer them after the talk. So please, enjoy this talk.
Hey, hello everyone. Thank you first of all for your stamina. You're still here. I hope this will be entertaining. This talk has 2 parts, and I will have 2 outlines, so watch out for that to keep track of where we are. Don't try to count the slides. Okay, so why am I here in the first place? I'm giving a talk about stars and planets, and the first thing many of you might think of is space colonization. There's a wiki on the EA forum that defines space colonization as the establishment of self-sufficient human settlements outside Earth. I will be talking even closer, like this. Cool. Okay. That's good for me because I'm losing my voice slowly. I'll be talking about interstellar colonization because I'm talking about exoplanets, that is, planets outside the solar system. That is the establishment of settlements outside the solar system. This wiki says further that, if feasible, this would raise the upper bound on the number of people who could eventually live by many orders of magnitude. So this sort of implies that happy sentient beings flourishing across the universe is sort of an utilitarian goal in this definition. Okay, let's run with it for a second. So imagine ourselves now, in the far future, having some permanent settlement on an exoplanet. Again, exoplanet, planet outside the solar system. Have to send humans there. And before we do that, we should send some infrastructure or build it there. We should send perhaps some exploratory probes. Before that, we have to do lots of engineering. And before that, we have to select a planet to go to, or any place. And even before that, we have to characterize these planets, so know what these planets actually look like. And, well, there's a step even before that, namely, finding one or multiple. All right, so on all of this, the timescales, to me, are entirely unclear. But I feel like these 2 parts should come first in that sort of cardinal order. And the good thing is, we're already doing some of that. And this is basically what the talk is about. Part 1, part 2. Okay. So the question that I'm concerned with in my research is, what is out there? What is out there implies a bunch of other questions. First of all, are there planets at all? Well, beyond the solar system, I mean. Are there planets like Earth? More precisely, where are they, if there are any? Are they habitable? And if they are they inhabited by anything? And if they are not inhabited, then there is the pressing question of why. All right, so part 1, exoplanet detection. We're going to talk briefly about the first exoplanet, then how we detect them generally, how many exoplanets there are today, and a bit on Earth 2.0. Okay, so again, what is out there? Out there is the first exoplanet, 51 Pegasi b, which is a hot Jupiter. You've never heard of a hot Jupiter before? Don't worry. This is 51 Pegasi. This is the host star, so the sun of this planet. It's about 50 light years away. To the naked eye, it's just about visible. And it's a similar size to the sun. This looks very unimpressive. This is just about any image we can take with a telescope. But if we were able to zoom in a little closer, we would see this. A Jupiter have the mass of Jupiter, actually, but we call it, it's a gas giant planet. Jupiter is the largest planet in our solar system, and it's surprisingly orbiting the star in only 4.2 days. So Earth is orbiting in 365 days, and the innermost planet in the solar system is orbiting around 80 days. So this is something that does not exist in the solar system. This was the first discovery by Michel Mayor and Didier Queloz, for which we got the Nobel Prize in 2019. And that was already a bit of a shocker because, again, we were expecting that the solar system is kind of usual, but apparently the first thing we find is something that we've never seen before. Interesting. How did we find it, though? So I'm going to show you 3 methods of how we find exoplanets. Imagine you're spinning around your like a small child. This would be roughly the same situation. You would be spinning, the child would be spinning, but you would not be spinning around your axis. You would be spinning, the axis of your spin would be slightly in front of you. The consequence of that for a star is that if a planet is around it with a sufficient mass, the star would go back and forth. And that would change the frequency of light coming at you. So if the star is coming towards you, it would appear bluer, and if it's moving away from you, it will appear redder. And that going from blue to red to blue again would be periodic with the orbital period of the planet. That's how we discovered the first one. So this is a very boring method because you don't get to see anything. A cool method is directly actually taking a picture of the planets. And this is a thing that you can do by putting a shade in front of your star. Because the problem with direct imaging is that the star outshines the planet by a factor of 1 billion, roughly. So you have to block the light so that your detector is not saturated all the time, and you can actually capture only the light of the planets. So this is what is done, and this is, in my opinion, this is the coolest video on the internet. This is 4 giant planets in wide orbits around a young star. So you see in the middle of the little star is where the actual host star is supposed to be. So, and you see the shade in front of it. There's still light coming around. This has to do with, diffraction, all sorts of physics, don't bother. But, we're doing a reasonably good job here. And what we see is these 4 planets here, 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 and here, over a timeline of taking like years. So this is amazing. The downside is that, as you can see here, the scale is 20 astronomical units. Our distance from the sun is 1 astronomical unit. So we would be, inside this plate. So with this method, we cannot find a second Earth yet. Okay, this method is called Planetary Transit. And the idea behind it is that a planet transits its sun. So you have the sun sitting here, and if you're watching from the right angle, the planet will be orbiting in your line of sight, which means every time it goes around, it will block a part of the sunlight coming from the star. Now it works. And so have an eye on what signature that produces. So you have the light over time being relatively stable until you suddenly go in front of a star, the light drops, goes back, and this pattern repeats every time the star goes around. So this is the method that found like 80% or more of all exoplanets that we know about. Okay. So we've seen the first exoplanet, which has been a surprise already. We've seen 3 different methods of how to detect them. This is how we're doing this on the ground. Now we want to know, well, what did we find? Did we find Earth? Not our own planet, but another one. That should not be loading because this is not even a movie. Okay. So this is a histogram of detection since 1995, the first discovery here, until 2023. This is from a week ago. And this is the number of exoplanets discovered in that year. So until 2009, we've been detecting exoplanets with the radial velocity method, which is bluer and redder and bluer again, until we launched Kepler, that started looking actually at only one patch in the sky, and then the numbers skyrocketed. This thing ran out of fuel in 2018, so we launched TESS, which is a little smaller, but it's like a cheap NASA thing that just popped out within a couple of years. So just basically 4 cameras on a satellite, but it's still detecting a bunch of planets. From this, we get 5,500 exoplanets as of September. No second Earth. This is a little unfortunate because Kepler was actually meant to find a second Earth. It was the whole selling point of this thing. But it turns out stars are not just uniform orbs. This is the sun. It is not a uniform orb. It's doing all sorts of things. These sorts of things we call stellar activity. It has to do with the fact that stars are magnetic and they produce explosions, they produce sort of this pattern, granulation, all sorts of, you see these magnetic loops down here. So stellar activity makes the star flicker. So if you put a planet in front of it, even if you have ideal conditions, your star will still be wobbling in your transit. This shape I was emphasizing earlier would look like this. So we did underestimate how much of a problem this would be because the sun is boring and old, and the stars we've been looking at are exciting and young for the most part. So that was unlucky. But what we got to do in that case is build a better and bigger telescope, which we did. We're building Plato at the moment, which is actually headquartered here in Berlin. This is what it looks like. It's in the testing phase, trying to shake it and see if it will survive the launch. Quite a big thing, bunch of telescopes on top. So the most conservative predictions say it will find another 5,000 in the next 4 years. It's supposed to launch in 2026, but that's very conservative. Rather likely is something like 20,000 more, and the prediction for Earth is actually that there'll be 10 to 30 planets with the characteristics of being, around Earth radius, around the orbit of the Earth, and orbiting a sun-like star on top of all that. So these are the most recent predictions. So to emphasize, we will likely find an Earth analog by 2030, which is wild to me. So how many exoplanets are there? Around 5,500. Many more to be discovered. Plato will likely find a bunch of Earth analogs. All right. So these are not the planets we're gonna, colonize. To me, if I'm being honest, this whole space colonization thing has a bunch of questions, not only with respect to technical feasibility, but also to moral desirability or even acceptability. But I have a better reason for you. This is why I'm here. So the better reason is that with these 10 to 30 Earth analogs, we can get empirical constraints on some existential risks. Not now, but in the foreseeable future. So I don't have to define existential risks to you. Just to reiterate, events that can wipe out humanity for good or, catapult us back to the Stone Age forever. Empirical constraints is meant to emphasize that we are not relying on models and the fact that we don't have anything to compare Earth to, but actually doing some empirical statistics. So let's look at a timeline of Earth's history and future. This is my timeline, time after formation of the solar system. At about 10 million years, Earth is forming. At about 9.5 billion years, Earth is engulfed by the star as it expands in the red giant. Somewhere in between, here we are, probably changing the surface of the Earth with climate change. And about 2.4 billion years ago, we had another quite remarkable event, which gave us an oxygen boost, where the atmosphere of the planet suddenly had 20% of oxygen very, very rapidly. What we don't know is what happens in the future. So we can build some models. We can built the toy model of a global catastrophe with permanent effects. This is from the book Light of the Stars by Adam Frank, who looked at population and planetary temperature as it evolves as we adapt our resource consumption or don't. One possible scenario is that over time, population grows beyond the sustainable limits, and then we run into a die-off sort of famine situation that reinforces itself. If you want to hear more about that, there will be a talk right after mine that I highly recommend, and the temperature rises accordingly. So stay tuned for the next talk if you want to know more. There's a more optimistic one where both population and temperature rise somewhat but stabilize, and we find a way to do it sustainably, but there could still be collapse if we don't adapt. Temperature will rise and we turn into a Venus, and humanity dies out. And this is a bit cynical, but implying that we try to change our ways, but it's kind of too late and we die out still. But these are still toy models. So ideally, we have this comparison sample of Earth siblings, some of which will hopefully look like Earth, and some might not, even though they should. So how do we use this? Now is part 2. We already looked at some major events in the planet's lifetime, this odd oxygen boost, the great oxidation event. Climate change could be another one. And we've noticed that soon we'll have this sample of Earth siblings to compare with. But in order to say anything about whether that is informative for us or not, we need to know their age. We need to know whether this planet is older than Earth or younger, because if it is younger, this is not of too much information, perhaps. We need a timeline. So I will tell you about how we measure age, and it's actually not that easy. We use open clusters, and I'll come back to that in a second, and stellar rotation to do that. And we also, once we placed the planet on the timeline, we want to, actually look into its properties. I will pick 2, there's of course more, but 2 that we have access to at the moment is mass and radius, and the other is atmospheres. All right, so this will be the second part. Okay, so if we look back at our timeline, we need the age. How do we do age? How old is the planet? Is the question. Well, it is of the same age as the star, which does not answer the question. Because now the question is, how old is the star? I can look at my own birth certificate, and provided I can read it, I can say when I'm born. But this is the first diagram any astronomer, any aspiring astronomer sees in their life that gives you the surface temperature of the star, and on the other side, it gives you the luminosity. It's just a way of classifying stars. You have massive stars on top, which are extremely unstable. So they live for a couple million years, which is, I told you we're 4.5 billion years old, barely anything. But the stars we are looking at, among them the sun and all the smaller stars, are extremely stable. The unfortunate thing about it is that, they don't change much. So what stars do is burning hydrogen in their cores. Once they're done, they enter this unstable regime and things go haywire and they end up down there. But they sit here. The sun sits there for 10 billion years. These stars sit here for 100 billion years and more. So it's hard to tell how old they are. But we have tricks. Okay, so telling stellar age is hard, but there's strategies. One strategy is open clusters. Okay, so an open cluster is a group of stars that formed at the same time, sort of like siblings among stars. And the second thing is that you can tell the age by the shape of this diagram if you can identify all the members of that open cluster. So an open cluster can look like this. This is the Pleiades. If you look at the sky, you can actually spot it. It's sort of a distinct little patch, and you can actually make out the blue ones. So back to this diagram, the Pleiades on this thing here, on this plot, look like this. So ignore all the background stars, so we identify the cluster. It's just moving together. It's in the same place on the sky. And it follows this shape here. Now, how does this help me? Now, the Pleiades are 120 million years old, which we can tell by all the stars up to this mass sitting on the main sequence. Stars of higher mass, they're not shown here, will have run out of hydrogen already and would have gone, all this haywire thing down to white dwarfs. We can see this a little clearer if we look at a cluster that is a little older. Looks similar, but these stars here are smaller, they take longer, but now they have started moving away from this main sequence and starting evolving really, really fast. So big stars evolve fast, and by the shape we can tell how old this is. This is a method that we have known for a while. Unfortunately, not all stars are in open clusters. The sun is not in an open cluster. So we use stellar rotation, and this is a relatively new thing. So I think for the first time it has been used in 2003 or so, where people really thought, well, we can use that as an age indicator. So stellar rotation predicts age, and I will show you how. And we use open clusters as benchmarks. So you see here, again, effective temperature gives you the size of a star in the rotation period in days. And we will compare different open clusters with each other. You have the Pleiades, again, the Praesepe, so the young and the older cluster. And then, these weird numbers here, these are more open clusters, and here just, general purpose old stars with their ages. Mega years is million years, giga years is billion years. What it looks like is like this. So if you pick a mass, say 5,000 Kelvin, slightly smaller than the sun is here, roughly, you see that if you are young, you're rotating at shorter rotation rates, and as you go up and slower, turns out you can tell the age, and we know from the open cluster method how old stars should be when they pass here, and then we sort of, with some sophisticated models, etc., we interpolate between here. So to put it simply, old stars rotate slower than young stars. All right, so this is how we tell age, and this is, I want to emphasize this, it's a hard problem still. So these stars here are quite a mess. And the oldest cluster here is 2.7 gigayears old. The sun is 4.5 gigayears old, so we're kind of struggling to populate this region. So this is an active region of research, and these small stars, let's not talk about it. Okay, suppose we get the age. Now we want to know the properties. So let's start with that. The thing is, if telling stellar age was hard, telling planetary properties is new and hard, because, well, the first planet has been detected just 3 decades ago or so. Okay, mass and radius and atmosphere is the two that I promised to you. Mass and radius is the first one, and I want to show you my favorite system, which is the Trapis I system. It has a tiny star in the middle. It's about 10% of the solar mass, and it has 7 planets, which are probably kind of rocky planets. Talk about it in a second. And some of them are in the habitable zone of that star. So this green region is the region where water is in its liquid form, which is the standard definition of habitable zone, which is debatable, but works for our purposes. So just to illustrate, this is the inner solar system with Earth here. This whole thing fits down there. It's tiny. And this star is much more common than the sun. So another crazy thing, I showed you with hot Jupiter. This is another thing we have never seen before. And it's been detected in 2016 or so. All right, so mass and radius. The thing about the Trapis I system is that it is a system with the best known mass and radius constrained at the same time. So this is, we use mass and radius in combination to tell what a planet is made of. This is the amazing thing we can do with mass and radius, to some extent. I will show you the limitations in a second. So we have, don't pay too much attention, this is the temperature of the planet. This is the planet mass in Earth masses. This is one Earth mass here, planet radius here, one Earth radius here. Okay, this looks messy, bear with me. You see Venus, Earth, Mars, and you see these letters, which refer to all these 7 planets. All of them? I think it's, yeah, all of them. Different temperatures. And these circles around are sort of our uncertainty about what the mass and the radius is. And now, the interesting part, though, is these lines, because these lines correspond to different compositions that would be consistent with this mass together with this radius. All right, I'm picking just some because these are too many. So the top here is an old star of which 5% of the total mass of the planet is in the atmosphere. This is ridiculously high. This is why nothing is on there. This here is, I think, 1/10,000th of the planetary mass is water in the atmosphere. This is still 4 orders of magnitude more than the Earth has. And it's compatible with some of these planets. So these could be sort of, so like sauna planets, I would call it. Old star, lots of surface water. If you've seen the movie Waterworld, this would be one. And many of these planets are actually compatible with being a water world. But many of them are also consistent with having, solar system compositions, being really similar to Earth and Venus. So this is already, we can exclude this crazy thing. We can say a little bit, well, this sauna planet seems kind of unlikely for many of those, but many other things we cannot exclude yet. So this is a very active branch of research, and we're moving towards being able to actually tell what the planet is made of. Okay, so it was a bit about mass and radius. Well, it gives us a bulk density, right? It does not tell us anything about the structure of a planet. The other thing we can look at is atmospheres. How does that work? Big word, transmission spectroscopy. Spectroscopy always has to do with looking at individual colors, at individual wavelengths of light. So white light, as you get it from the sun, is composed of all sorts of wavelengths. If you put it through a prism, you get red, blue, green, etc. So spectroscopy is looking at these colors individually. And how it works is, well, we have incoming starlight from the sun down there, and it passes through the atmosphere layers of a given planet, and some of that light survives, some of that light is blocked. And by comparing the starlight when the planet is in the way versus versus the star when the planet is not in the way, we can tell what is in the atmosphere by interpreting what light is blocked out. Okay, so it's all about the surviving starlight. Sometimes we don't need to look at all colors, at all wavelengths. Sometimes it's enough to look at a single wavelength to find something very interesting. So in this case, we'll be looking at a planet losing its atmosphere while we watch it. So we've seen the planetary transit. This is why I wanted to explain to you this method. The planetary transit in broadband white light, all wavelengths, looks roughly like this. So the planet is coming in front of a star, blocks out part of the light dips down, the star becomes a little fainter for a moment, and then it goes back. The feature I want you to pay attention to is it's symmetric. Now, if we look at it in hydrogen wavelengths, so the color of hydrogen atoms, the transit suddenly looks like this. This is not symmetric. But that does not mean that the planet suddenly turned into a football. It just means that it has an extended hydrogen atmosphere. And that is nicely depicted here. So we're watching this planet orbiting its star. And since it is very young, it has its sort of primordial hydrogen atmosphere. And while it's orbiting, the stellar wind is blowing off the atmosphere of that planet. Whatever is left has, well, will in some million years have no such atmosphere at all. And a second one can emerge. So a secondary atmosphere that might be Earth-like. We can look at all wavelengths, and then we have something like this. So we have different wavelengths here, and how many light sort of blocked out by the atmosphere. And this is a hot gas giant, like the first planet I've shown you. And you see that it has water, it has CO2, all sorts of things in there. You might wonder, well, I don't care about gas giants. I cannot land on a gas giant. I want a planet to colonize. Well, this still tells us a lot, because this is sort of a concentration of the stuff that makes up this solar system. So looking at those is very interesting. Unfortunately, we only have like 30 to 40 measurements so far of planets in this transmission spectroscopy way, but the James Webb Space Telescope that launched not too long ago is revolutionizing that. Back to Trapis I. And, well, these are possibly terrestrial, and we're watching them with JWST. The innermost planet, I'll just give you a hot take on that, which is really a hot take. The innermost Trapis I exoplanet is hot and airless. Bad luck. But that was expected because it's so close in. It's inside the habitable zone, and we think a similar thing happened as with the system I showed you before, just the whole atmosphere has been blown away. All right, but E is in the habitable zone. I wish I could show you the results, but we're still waiting for the detections to come through. So this is sort of happening right in the moment, and I'm on the edge of my seat about it. So it's on the schedule of JWST. This is a screenshot from the schedule, from the actual schedule. And you see the plan windows for observations of Trapis I. Some of them already happened, some of them are still to happen in October, so stay tuned. This is gonna be exciting. This is not an Earth analog yet because the whole star is so tiny, but it comes closest. So, summary of the second part. We've seen that major events in the planet's lifetime can change the appearance quite a bit, and for good. We know that soon we will have a sample of Earth's siblings, and we can tell that we have methods to tell their age that are continuously improving, stellar rotation being one of the strategies to employ here, and we can already measure some properties, so mass, radius, bulk density that probes the interior structure, tells us how much water there could be potentially, and atmospheres that are currently available only for gaseous planets at the moment, but stay tuned for the terrestrials. Okay, if that got you interested in exoplanets, short overview of what you could do if you are so inclined. You could directly work on the problem, do a bachelor, something like physics, space engineering, biology, geology, then add on a master with something with astrophysics inside, either as a dedicated program or as like specialization. You could do a PhD in a related field. I had a lot of fun doing one. Astrochemistry, astrobiology are very new fields that have been, basically opened within the last 5 to 10 years or so, haven't existed before. Exoplanet characterization, also a thing. Space engineering, if you're more interested in building the next JWST or the next Plato telescope, or a big telescope that can actually do direct imaging of terrestrial planets, that would be amazing. You can continue in academia or work for a space agency. These are Europe, US, Germany, and Europe. And France has CNOS and whatever. Talk to me about it if you want to. Indirect methods could be policy work to increase funding. I need funding. Public outreach, science communication. Okay, so to summarize, because we are at 40 minutes, main takeaways. So timelines for interstellar space colonization are unclear, at least to me, but finding and characterizing exoplanets is definitely, anyways, the first step, I think. Astronomers are finding exoplanets at an increasing rate. Detection of a second Earth is sort of, for my timelines, it's very, very soon. And with a sample of Earth siblings, as I argued, we will, for the first time, be able to empirically compare different planets that could be in the future of Earth, and test the probability of extinction events or catastrophes with permanent effects. So how many Earths are actually turning into Venuses for reasons? And if you don't buy any of that, I hope you at least buy that characterizing exoplanets is kind of new and cool, and it's a lot of fun. And there's a lot to discover and will be discovered, and we will get a lot of surprises like hot Jupiters and tiny systems in the future. So with that, I stop and take your questions if you have any.
Amazing. Thank you so much for this wonderful talk. So do we have some questions in the swap card?
We do have a question right here in front.
Okay. There is one appearing now. Was it you or no? Okay, so you can ask it, but please speak loudly so everyone can hear.
Thanks a lot. Very interesting talk for a lawyer. And just a question on the idea that we detect all the Earths to then figure out what happens to our fusion. In the timeline, you say Earth is 10 million years old. So do we hope to have a planet that's between 0 and 10 million years? Or?
No, I was actually trying, so I'm not sure, you can probably still read it, right? Earth is 4.5 billion years old. We formed 10 million years after the sun was formed. So it takes a little bit of time to, put all the dirt in a big sphere and make an Earth, and that's about 10 million years. So we are hoping to find, so I hope to find stuff that is both younger and older to understand, well, Earth's past and how it came about. Did other planets have a great oxidation event or not? But also whatever happens in the future.
Good. So we have a question from Niklas. Could you talk more about how observing planets informs our estimates of existential risks or informs our understanding of the Fermi Paradox?
Ooh, yeah, the Fermi Paradox, my favorite. So the Fermi Paradox, I think I've answered that first, is a thought experiment that is very unconstrained. And I know people in the effective altruist space have been trying to answer that question, but it has a lot of assumptions about advanced civilizations and how they behave. Depending on what your view of what a future civilization is more like Star Trek, or is it more like these grabby aliens situation where you just try to harvest as much space and energy from the universe as possible, you will get wildly different results. And what we can do with these exoplanets is actually looking for technosignatures, which is something I did not talk about, but is very interesting. It is a very new field because it had this stigma of science fiction for a long time, and it is still slowly coming out of that corner. So I'm hoping for people to look more into that, and it's becoming more and more possible, and particularly with machine learning methods that are flooding astronomy, allowing you to look at a whole bunch of data and just look for stuff that sticks out from the mass, and that is one of the ways we're trying to characterize exoplanets. And the first half of the question was
relating to our understanding of existential risk.
Right. So I'm pointing at this direction very vaguely because I'm not trying to make any claims on, what the result will be. This is very much exploratory. So I cannot do, an expected value calculation or, predict how much, like what we will find in this question mark. But I think regardless, it is worth going there and finding out. So that's all I can say to that.
Okay, Niklas, if you have a follow-up or not, then do we have some other questions?
I think there was.
Yeah, please.
Yeah, I wondered, is in the EA space, so the space people who are also in EA, are they also talking about like satellites breaking down, other satellites which will cause this chain reaction of satellites breaking down, and what are some of the solutions proposed
Yeah, so
to solve that?
I want to say I'm not a space engineer. I'm not like an expert on these things. So if the thing you're referring to is a Kesla Syndrome. For the rest of you who might not be familiar with it, if you crash two satellites or a satellite crashes into something, bursts into thousands of pieces, these pieces move at tens of kilometers per second through the Earth orbit, crashing into other satellites. Those bursting into thousands of pieces, and you see the cascading effect, everything turns into dust, and we have no satellites at all. That would be bad. And there's a bunch of technological proposals on how to solve this. I'm not sure, this is something I do not know, how far along they are actually in implementing those things. What I know is that the American Association for, that authorizes launches, just authorized to launch like several tens of thousands of more Starlink satellites. And those do crash. And I know 40 of those crashed recently, fortunately during launch, just because during the launch, people were not paying attention to the sun flickering, basically. So, yeah, it's a problem, and I think there are solutions, but it's a disaster waiting to happen, and I do not know how active people in EA space are working on that.
Okay, we have two more questions in the swap card. From Christopher. We find temperature and climate change and mass extinction records with ice core and fossils. But you only get a snapshot of past time from signature. Right? How would we understand the process of change with a snapshot? So, could you perhaps? But yeah, I don't know whether it pertains to the subject of this discussion.
Yeah. So, well, if I understand this argument correctly, so from ice cores we basically look into the past because our ice is piling on top of each other, and whatever is enclosed in the ice gives us sort of a timeline from Earth's past. But if we look into atmospheres from planets that are older, we only get snapshots from a single point in time. That is correct. The solution to this is looking at multiple planets, which also gives you a timeline which you hopefully can interpolate. Sure, for the Earth's past, we have also other ways of telling what happened. Otherwise, we would not know about this great oxidation event. But it will tell us how likely it is to happen in other places. So how much of an exception we are. So that's still kind of valuable, even though it is not as accurate as ice cores.
Yeah, that makes sense. Do we have some more questions? Or was it a follow-up?
Okay, that's multiple questions. I will try to still answer the ones I remember. Okay, so when do we reach statistical significance? Depends very much on how strong the signal is from any individual planet. It might be enough to probe, 5 to 10 planets if they happen to line up on a timeline, 4.5 billion years, Earth, 4.75, 5.567 billion years, and at some point, all the planets up until 6 billion years or so, this is very fictive, but just as a thought experiment, every planet is green and nice and looks like it has plants and whatnot, and everything after 6 billion years is dead. That would be significant, and it's enough to have 5 to 10 planets. The difficulty is to characterize them and have them characterized well enough to actually tell both the age and these properties. So the planets that we will find, these second Earths, might be at very different distances, which makes it harder if they're far away, or easier to characterize them. So the timelines for doing that are, I think, anything between, I would say, 20 to, if we're very unlucky, maybe 70 years or so, maybe 100 if things go very wrong. But the good thing about astronomy is 20 years ahead, sometimes even more, what instruments are going to be out there. And so I'm relatively optimistic that we will have, in the timeline of something like 50 years, a good sample. If there is something really catastrophic, this turning from green paradise to Venus or something, if there are more subtle things, we will have to look for longer. So that is roughly does that answer your question?
And that relates perhaps to another question from Greg, whether would nuclear war be detectable from spectroscopy?
Well, depends on the consequences, right? The thing about, so again, I advertised the upcoming talk, which features an expert on nuclear war. But I happen to be involved in that work, so I know a bit of it. The thing about nuclear war is the duration of the permanent effect of the effects on the atmosphere are transient. In even for now at least, the biggest nuclear war that we can imagine gives us a nuclear winter of about 10-ish years. That is kind of nothing. So the nuclear winter itself would probably not be detectable unless we have thousands and thousands of exoplanets. So might be something we can do in the future, but for the next decades, it's probably out of question. But if it leads to, if it burns down, because fire is one of the things that causes nuclear winter, if it burns everything, then we suddenly have a drop in, we don't produce oxygen anymore because all the plants are dead. We will notice that. If it, stays like that and life does not re-emerge.
Good, great. I think that's all what we have time for now. And if you want to chat more with Ekaterina, you can see her at the office hours she's holding in 5 minutes next doors in Kepler. So yeah, feel free to reach her there. And now, yeah, we can please join me in a round of applause one more time for her.
Thank you.
Thank you.
Thank you for your questions also.